Okay, let's dive right into this. Welcome to the explainer. It turns out the components hidden away inside those electrical panels are exactly what keep entire facilities running safely. Today, we're taking a really close look at the true backbone of these systems, the bus bar. We're going to unpack the hidden complexities of how they're designed, why they actually fail, and what literally keeps them safe.
So let me ask you, what is the absolutely most critical conductor in your electrical panel? Often people think of bus bars as just these simple passive blocks of metal, just dumb copper or aluminum rails sitting there doing nothing but conducting electricity. But actually, scratch that, that is a massive misconception. A bus bar is a highly engineered component. It dictates thermal performance, fault withstand capabilities, the physical footprint of your panel, and most importantly, the safety of the maintenance teams working on them.
Here's a quick look at our roadmap. 1. The heart of the panel. 2. Surviving the short circuit. 3. Architecture and safe distances. 4. The weakest link. Joints. And 5. Standards and verification. All right, Section 1, the heart of the panel, going beyond simple ampacity. We really need to look beyond just simple ampacity to understand the foundation of a switchgear assembly. By definition, a busbar is the low-resistance main conductor rail that takes power from the incoming supply and distributes it out to the functional units or feeders. But what's genuinely fascinating is that compared to your standard cables, busbars are used in these high-current, low-voltage panels because they offer way lower impedance, much better mechanical restraint, cleaner routing, and far more predictable behavior during a short circuit. They effectively manage heat flow and honestly allow for a much more compact panel footprint. When designing these systems, the big material showdown is almost always between copper and aluminum. And this brilliantly illustrates the real-world trade-offs engineers have to make. Copper is pretty much the default. It's got about 100% IAS conductivity, lets you build highly compact layouts, and offers incredibly strong joint stability. Aluminum, on the flip side, sits at about 61% conductivity, which means it needs a larger cross-section to hit that same resistance. But it gives you a much lower mass and material cost. That weight reduction comes with a catch, though. Aluminum requires much more demanding joint practices because of this rapid oxide film buildup. Now, when you're sizing copper bus bars, you might think it's just a simple formula based purely on the cross-sectional area, right? Like a 25 by 3 millimeter bar handles about 200 to 250 amps, while a beefy 60 by 10 bar handles roughly 1,200 to 1,270 amps. And sure, rated continuous current is definitely the starting point, but here's a truly fascinating fact. Pure area-based rules completely lose their usefulness at larger sections because of the skin effect and proximity effect. High frequencies and larger conductor sizes actually change how the current flows. That means things like enclosure heating, ventilation, and fault duty heavily dictate the final size. Moving right along to Section 2, surviving the short circuit, the paradigm shift. Surviving a short circuit requires a complete paradigm shift from everyday continuous current to examining a highly destructive environment. Remember what we just discussed about sizing? Well, cross-section alone never tells the whole story. So the crucial point is this: a bus bar that effortlessly carries its continuous rated current without overheating can still fail catastrophically during a fault check. Short circuit performance demands we look at two entirely different types of destructive stress. A short circuit unleashes two highly destructive forces. First up is the thermal withstand, or ICW. Think of this as runaway, invisible heat, the adiabatic I²T energy that rapidly heats the bar during that split-second clearing time before the breaker trips. Second, we have the dynamic withstand, or IPK. And this isn't about heat at all. It's about sheer physical violence. We're talking about peak magnetic Lorentz forces between parallel conductors that physically push, pull, and literally try to tear the conductors and their supports apart during the very first current peak. To wrap your head around just how massive that dynamic physical stress actually is, just think about this multiplier, 2.2. In IEC-based low-voltage practice, engineers often use this as a practical approximation, where the dynamic peak current, IPK, is roughly 2.2 times the thermal current, ICW. That means the dynamic force ripping at the bus bar supports is exponentially higher than the baseline fault current. This is exactly why support spacing, bar stiffness, and cleat strength are just as absolutely crucial as the copper's thickness. Okay, Section 3, Architecture and Safe Distances, Routing and Separation. Handling these incredible electrical and mechanical forces means we have to organize these components safely through some really strict layout and spacing rules.
When we talk about safe distances, there is a natural dichotomy that we must never confuse. Clearance is the shortest distance between two conductive parts directly through the air. This protects against an air gap flashover. Creepage, however, is the shortest path between two conductive parts along an insulating surface. This protects against a surface tracking failure. They solve entirely different failure modes, so you definitely don't want to mix them up. The required creepage distance isn't just some static number either. It depends heavily on the environment, which is classified by pollution degrees. Consider the jump from pollution degree 2 to degree 3 at 400 volts. The required surface creepage distance almost doubles, going from around 2 to 2.8 millimeters all the way up to 4 or 5 millimeters. Why? Because environmental factors like conductive dust, humidity, and condensation in an industrial workshop or motor control center significantly increase the risk of electrical tracking compared to, say, a pristine, clean electrical room. Beyond just spacing the bars out, we also have to separate the compartments they sit in. Forms 1 through 4B describe this segregation. Form 4 separation isolates the bus bars, the functional units, and the terminals completely from each other. This radically improves safety for maintenance workers by preventing accidental contact with live parts, and it stops a localized arc flash from spreading like wildfire. But as you might guess, putting in all these physical barriers significantly adds to the panel's cost, its size, and the overall layout complexity. Which brings us to Section 4, the weakest link, joints, where most failures begin. All right, here is a massive narrative twist for you. Straight, continuous conductor bars, they almost never fail. The failures almost always begin at the joints. When a joint fails, it's usually because of a few sneaky villains creating runaway heat and resistance. We're talking loose hardware, long-term material creep, uneven contact pressure, and dissimilar metal galvanic effects, like when someone improperly bolts copper directly to aluminum. And we absolutely cannot forget rapid oxidation films. Aluminum joints are particularly high maintenance here, as their oxide films form super fast and will just destroy the joint's conductivity if they aren't prepped right. Defeating this contact resistance takes strict discipline through a really practical pre-delivery checklist. Step 1, you've got to verify the contact faces are completely flat and clean. Step 2, confirm you're using the correct hardware and washer stack. Step 3, apply an approved joint compound on those demanding aluminum interfaces. And finally, Step 4, recheck the torque using documented, tested manufacturer values. Stable pressure keeps resistance low. Unstable pressure creates heat. Simple as that. But, even with a flawless installation, things can loosen up over time. That is exactly why infrared thermography is widely treated as the modern hero of electrical maintenance. Periodic IR inspections under a meaningful load allow technicians to actually see the invisible hotspots forming at failing joints or overloaded sections. It's a real game changer because it lets them fix the issue long before it triggers a catastrophic shutdown or an arc flash event. And finally, Section 5, Standards and Verification. The rule books that keep us safe. Let's zoom back out to the macro level for a second. Designing a safe busbar system isn't just about applying pure engineering theory. It's all about adhering to rigorous international frameworks. We've got the IEC 6439 series for the switchgear assemblies themselves, IEC 6080-65 for short circuit calculations, and IEC 6064 for insulation coordination. Over in North America, UL 891 plays a very similar assembly-level role. Now, what's really interesting to note here is the core philosophy. Design verification belongs to the complete assembly. You literally cannot just declare a generic fault rating based on an isolated copper bar. That declared withstand capacity has to be verified for the conductors, the supports, the enclosure, and the joints all working together as one tested system. Wow, we've covered a ton of ground today, from the violent Lorentz forces of a short circuit down to the microscopic oxidation films ruining an aluminum joint. The engineering behind low-voltage bus bars is layered, it's complex, and it is absolutely vital for facility safety. Which leaves us with one final provocative question to consider regarding your own infrastructure. What hidden hotspots are lurking in your panels right now? Thank you so much for joining me on this explainer, and keep learning.